Quantum causality, a potential fix for physics' deepest flaw. The link between cause and effect is so ingrained in our understanding of the world that it seems self-evident. Yet, when physicists delve into the bizarre realm of quantum mechanics, the physics of atoms and subatomic particles, this fundamental connection breaks down. For decades, the observer problem has haunted quantum theory, the unsettling idea that reality isn't definite until someone observes it. Now, a new approach suggests a radical solution. Causality itself may be the deepest layer of reality, resolving quantum paradoxes and potentially paving the way to unifying quantum mechanics with Einstein's theory of general relativity. The quantum measurement problem, quantum mechanics, is remarkably accurate at predicting experimental outcomes, but it struggles to explain why things happen the way they do. Before measurement, a quantum system exists in a superposition, a fuzzy mix of possibilities described by the Schrödinger equation. The act of measurement collapses this wave function, forcing the system into one definite state. This raises a critical question: what constitutes a measurement? Does it require a conscious observer? If so, what defines an observer, and how does observation create reality? Many physicists find this unsatisfying. As Nick Ormrod of the Perimeter Institute puts it, the current situation with quantum mechanics is that it's a theory that predicts very well and explains very badly. This vagueness makes applying quantum theory to scenarios without clear observers, such as the early universe or the structure of spacetime itself, deeply problematic. Reinterpreting quantum reality through causality instead of clinging to the ill-defined concept of observation, some researchers propose that causality is the primary driver of quantum events. Two existing interpretations, consistent histories and relational quantum mechanics, offer partial insights, but they have flaws. The consistent histories interpretation suggests that all possible evolutionary paths of a quantum system are valid, but doesn't explain which one we actually experience. Relational quantum mechanics posits that properties only exist in relation to an observer, but lacks a rigorous mathematical framework. To overcome these limitations, Ormrod and his colleague Jonathan Barrett have developed a new framework rooted in quantum causality. This approach treats quantum systems as networks of causal bubbles governed by specific mathematical rules. Within these bubbles, interactions determine how systems evolve, eliminating the need for external observers to dictate outcomes. This isn't just philosophical speculation. The framework predicts the same results as standard quantum theory, but without invoking the mysterious power of observation. It suggests that causal structure is more fundamental than the properties we perceive, much like a spider's web. The threads, causality, come first, and points properties emerge from their intersections. Resolving paradoxes and unifying physics, one striking demonstration of this framework's power is its resolution of Wigner's friend paradox. This thought experiment highlights the apparent contradiction between two observers experiencing different realities. The causal interpretation sidesteps this issue by asserting that definiteness isn't absolute, but relative to causal structure. Observers within different bubbles experience distinct outcomes, but neither perspective is inherently correct. Both are valid within their respective causal frameworks, but the implications extend beyond quantum paradoxes. The notion that causality underpins reality aligns with insights from general relativity, where gravity is understood as spacetime warping caused by mass. In fact, knowing the causal structure of spacetime allows you to reconstruct its geometry. This suggests that spacetime itself might emerge from causal order, offering a potential bridge between quantum mechanics and general relativity. If causality is indeed fundamental, unifying these two pillars of modern physics may not require inventing new entities, but rather recognizing that the existing ingredients are arranged in the wrong order. The causal approach proposes a simpler, more elegant solution. Reality emerges from the fundamental relationship between cause and effect. Conclusion: the new causal interpretation of quantum mechanics is still speculative, but its ability to resolve long-standing paradoxes and offer a pathway toward unification makes it a promising avenue for future research. By elevating causality to the foundational principle of reality, physicists may finally unlock the deepest secrets of the universe.